Today we're looking at the 2019 game and specifically 5460's robot from Destination Deep Space. So this is back before the COVID shortened season of 2020. And so now we're getting back to where Swerve was less popular, and a whole lot of the technologies and things were just different. So as we look through the robots, the motors and things teams were using, a lot of the stuff is going to be a little bit different as you start getting back 19 and before. Uh, so let's look at the game first, like we've been doing. So this game was Destination Deep Space, presented by the Boeing Company. This was one of the first games that had a title sponsor, and so several of our students insisted that we refer to it as presented by the Boeing Company at all times, or DDSPBBC, BTBC. Sorry. All right. Oh, hold on. We have it already here. All right, there we go.
Welcome to the 2019 First Row Robotics Competition and this year's game, Destination Deep Space, presented by the Boeing Company. Two alliances of deep space travelers race to place hatch panels on their rockets and cargo ship, load valuable cargo for transport off the planet, and return to the safety of their habitat, all before the next sandstorm sweeps through. Each alliance has 2 rockets, 1 cargo ship, and a habitat. Hatch panels and cargo are available through the human player stations, and cargo is also available in the depots adjacent to the habitats. Robots start in their habitat and may be preloaded with 1 game piece. Alliances may also choose to preload some bays of their cargo ship with either hatch panels or cargo. During the first 15 seconds of each match, driver vision of the field will be blocked by a waning sandstorm. So robots must be controlled using either autonomous code or manually with a vision system on the robot. Alliances earn points for exiting the habitat, securing hatch panels, and any cargo that's properly stored. Cargo not secured spills from the cargo ship. As the sandstorm ends, driver vision returns, and alliances continue to earn points by loading their spacecraft. Alliances earn a rank point during qualifying matches for completing 1 rocket with hatch panels and cargo. Near the end of the match, robots return to the safety of their habitat for the upcoming launch and to earn more points. The alliance that earns the most points wins the match.
All right. So this game is kind of your modern example of a pure pick and place game. So what we mean by that is you're just not launching the game pieces, right? You're picking up game pieces from one area and placing them, scoring them in some part of the field. Um, what that means for this game is you basically had a few tasks like you do in every game. This one had more options than we've had in the past of how you could build a robot and still be very good at the game. If you look at all the scoring locations, all of the low scoring locations, the ones that are on the cargo ship, and the low goals on the rocket are all the exact same height. So there is a ton of scoring locations at the low level that don't necessarily require you to go up. What this meant was you had some competing incentives based on the way the rules were, that to get the ranking point for finishing a rocket, you needed to be able to score in the mid and high level. But to necessarily win the match, you didn't always need to do that. And so that led this year to having quite a few teams choosing different ways to necessarily play the game. So the vast majority of your higher level teams were going to do everything like they always are. They're going to build something that can score in the top level. But there were a few who, including one of the world champions, who weren't able to score the top, or even some of them who weren't able to score the mid, but they were planning to just be extremely fast at the low, or to be able to do the mid, because that means you just only had to have like a single stage elevator instead of double, and you could simplify your robot. And so there's times where you can make those trade-offs in certain games. A lot of times it is somewhat risky to do that early if you have the capabilities to do more. And so it just kind of depends on what you're trying to do. But there are games, this one specifically, where there is some value in not doing that. But if everybody chooses to not do that, then you run into a problem. You can't get that ranking point ever. You can't rely on your partner to get the top level. So there ends up being a lot of back and forth and having to decide exactly how you want to play the game, and your resources as a team to decide what to do. Um, yeah, for the most part, though, we are going to be picking up balls from the floor. It didn't make too much sense to only pick up balls from the feeder station, just kind of the way the feeder station worked for balls and the fact that you needed the cargo or the balls from the floor here anyway. The vast majority of teams are going to design to have a ball pickup. If a ball drops or bounces or one of your opponents rolls over to you, there's lots of times where you kind of really want to have that ball intake. So it was a pretty key, important part of this game was being able to ball intake. Hatch panels were a different story again. You had some options with either only picking up from the feeder station or being able to pick a hatch up off the floor. Um, it ended up being that the floor pickup wasn't super useful. There were a few teams who definitely made it work pretty well. There were even a couple teams who only floor picked up. They figured out how to get the hatch to drop out of like the cargo exit so they could pick it up from the floor. But the vast majority of teams largely only picked up the hatch from here and just made sure they scored it as much as possible. And if they dropped it, the time difference from going back to here compared to having a whole mechanism just in case you drop a hatch wasn't really valuable for most teams. So it wasn't ended up not swinging a ton of matches. Um, and then you need to be able to score in level 1 and 2 for the most part, and then possibly 3. The vast majority of the top level were scoring in all 3 levels just so they could guarantee that ranking point for themselves. And then the end game was also another place where you had multiple options. Level 1 was extremely easy. You could just drive up onto the ramp. Level 2 and 3 got potentially progressively harder, um, or just difficult in either way. There are a few different ways teams could do it. We'll look at one from a team from 5460, but this is one of those very unique end games that definitely is worth looking into and seeing how a bunch of teams solve the problem. You are also able to put multiple robots on any of the platforms, so fitting more than one robot on the top platform got you even more points. So there were quite a few teams who figured out ways to do that. Um, so there's a really hard engineering challenge, and just a lot of creativity went into how do you get robots to either do a two 6-inch stairs or one 12-inch stair. And so you had to decide how you wanted to get up there, how fast you could do it. This is also the game where you had people suction cupping off the top of this, so you ended up like suspending your robot out in front of it and still being supported by the platform. So there are a lot of really unique ways you could do this end game, and it's one of the ones that we look at a lot for innovative ideas. So if we ever have any sort of stair climb or platform climb again, a lot of the 2019 robots are going to come back up. Okay, so we're looking at 5460, and we'll see a match from them before we dive into their CAD, which I actually don't have their CAD open, so we're going to do that live real fast because I have it and we can get signed in. Okay, so we can have it rendering before we pull up their match video. Of course, it's not there. All right. Other teams' robots. 2019. 5460. All right. So let's look at a match for Strike Zone. So they're starting on level 2 in blue over here. And so depending on where you started, you could get more points by dropping down from level 2 to start. This ended up being pretty difficult for some of the Auton robots. There were some teams who could do it, but a lot of times you were doing this if you were using the Sandstorm driving, so you're driving with a camera. And this ended up being pretty close to top level. Most people, were, even in Auton, were only scoring 2 game pieces, and you could do about the same with a camera as well. There were some people doing 2.5 or getting close to 3, but it was pretty difficult, especially with just the way the software and stuff was back then. Again, we didn't have April tags, we didn't have motors with encoders all built in, or we weren't using them as well yet. The path planning and things weren't all out and published and open source the way they are now. So Sandstorm was a pretty useful advantage to be very low effort, and with some practice and well located cameras, you could do your double object pretty easily. So you only had that one defender here. So in this match, they chose to defend 5460. Again, most robots weren't swerved, so defense was definitely a lot easier to slow teams down. Yeah, so they have the ability to kind of move around their arm so they can score from either side. All right, so yeah, so then their defender kind of backed off. It allows them to keep scoring on the far side. A lot more teams were able to play picks and things, so they're pushing away the defender to allow the other team to go in there and score faster. So yeah, so they got the RP there with the top rocket, so they knew that they had that finished, and so now they're going to do their end game climb. All right, so then they got 3 teams up. The other team got to level 2, and so they were able to score a good amount in that match, take the win, and get their RPs. All right. So we can go ahead and actually look at the robot a little bit. As OnShape tries to finish loading, hopefully. All right, there we go. Okay, so similarly to most robots, we're going to divide them up into mechanisms. We're not going to spend too much time looking at the drivetrain here, but this is basically a relatively standard, what's called a West Coast drivetrain. It was one of the kind of standard tank drive styles that you would see. It was basically based on the 2x1 aluminum tube in a square frame, and then you had your wheels cantilevered out to the outside. So basically, only one side of the wheel was supported by the bearing blocks on the tube. And so the other side, if you didn't have the bumpers on, you could just like unbolt this, take the wheel off, swap in the next wheel, and be ready to go. So you had these like built-in, you had these bearing blocks that you built into the tube, and you bolted through, and those were supporting your drive shaft. And so then you'd have chain and sprocket going from your single gearbox back here. And in this case, they would chain from here to the middle axle, and then I think they ran a single chain from this pulley, from this sprocket all the way down to here. And so that meant if any one chain went, you only lost a single wheel. And so you would build in things like redundancy like that, but you were still powering all of this side from one gearbox and all of this side from the other. In this case, their drivetrain, because we didn't have, this is the first year Neos existed as brushless motors, and so we didn't have the efficiency that we do from motors now. And so in this case, they were running 6 mini sims on each side. A mini sim is a little bit shorter than a full size sim. It's about the length of a Kraken nowadays. And so that motor was a little bit more efficient in the way it was built. It had a little bit better internals with ball bearings and things. And it dissipated heat a little bit better when you had 6 of them compared to just 4 regular sims. And so this was a pretty common drivetrain, even though it was definitely a little heavy compared to some other things you could do. They still had a good amount of power. They weren't going to be power limited really with anybody else. In addition to that, they were running a shifting transmission. So because we didn't have these super efficient motors, they were using this gear shifter here to choose which gear ratio they wanted to actually output to the wheels. And for that, you would normally be able to have a very low gear that you could use to like push through a defender, and then you would have a normal driving gear that was your high gear that you could use when you needed to go a little bit farther down the field. Um, so if you needed to do a full half field or more sprint, you would be up in high gear. And then for a lot of times autonomous or just being able to push or get around defense, you would shift into your low gear. Um, and engage that. So they needed pneumatics to be able to do the shifting. So these are little tiny pancake cylinders that they have air pressure. We haven't really talked about pneumatics too much, but they're able to just push air in this like backside to push the cylinder out, and then push air in from the inside to pull it back, and they can choose which ratio they're in. Again, these are all things that we don't really have to do anymore with Swerve and with brushless motors. We're able to get way more drivetrain efficiency and kind of abilities without the need for shifting gearboxes or multiple motors all driving wheels or anything like that. Um, Very basics of how it turns, because I don't think we've actually gone over that, which is one of it used to be like the first thing we ever talked about, but we don't even have robots that do it anymore. Um, so one side you could drive one way, so if this drives driving forward and this side is driving backwards, then the robot's going to spin counterclockwise from the way we're looking at it. And if you do it the other way with these wheels on this side driving backwards and these drive forwards, then the robot's going to spin clockwise. And so you could vary those and you can make it do different arcs and things, but there's no way for it just to drive sideways like you can with Swerve now. Um, Everything else is relatively similar to Swerve robots. We still have the same like 2x1s. In this case, they're running their belly pan a little bit high, so they mounted the belly pan on the top side of the 2x1 to get their electronics up here. These are the older control systems, so this was before we had the Rev PDH. This is all the CTRE, PDP, I guess 1.0 now. The pneumatic control module, voltage regulators, this is how you powered the radio before we had the radio power module, and then now we'll just power it directly from the battery on the new radios, so we can get rid of even more connectors and hopefully be even more reliable. And then all of these devices are the separate motor controllers. So instead of having integrated motor controllers on the back of all of our brushless motors with the Krakens, or on the front with the Neo Vortex and Spark Flex, you had a bank somewhere on your belly pan where you had to wire all of these motor controllers in. They would get power, and then they would run the outputs from the motor controllers out to each of these motors. And so you ended up having to space claim quite a bit. And this is the same way that like Spark Maxes work with Neos as well, or a few of the other now standalone brushless motor controllers that exist. But it does end up having a few more connectors, a few more places where things could fail possibly, instead of just having the motor wires going straight into the motors and with CAN. You don't have like encoders built into these gearboxes at all or anything like that. And looking at it, I don't see any in their CAD. Doesn't mean they don't exist, but it doesn't look like they do. So it doesn't look like their drivetrain had encoders at all. So there's no way to know how far you drove. And a lot of teams didn't. So if you were just using Sandstorm, you didn't really need them back then. But you couldn't do velocity control or position control or any of the stuff we do nowadays that we just kind of take for granted. Okay, so drivetrain out of the way, we can look at kind of the rest of their subsystems a little bit. So they have an elevator here, and then they have a swing arm or a pivot or whatever you want to call it that allows them to score both from the front or swing around and score from the back. And then they also have a ball intake, which I think is here, so we can look at that. So looking at it, it was about as basic as you can get pretty much. There's not a ton going on here. It's basically a parallel 4-bar. So we talked about 4-bars before, but in this case, they're not quite parallel, just close. See, does that. kind of. I want this flat. That's better. Okay, so those don't look quite parallel. Those are off by a little bit, so it's a little bit off of a perfectly parallel system. We can see what that angle is. Yeah, so it's like 3.7 degrees when stowed, so it's not exactly parallel. Which means it's not going. This arm is not going to stay parallel as it extends and retracts, but it's not going to be off by too much. With these arms being relatively similar lengths, 9 inches and 8.625. Yeah, so they're relatively similar lengths. They're going to have a relatively similar profile to where this is going to stay not exactly straight at this level, but pretty close. If these are exactly the same lengths from pivot to pivot, and the distances here were equal, then this would just stay at that angle the whole time as it moved in and out. But this will change angle a little bit as it goes in and out, just because you have that slight difference in lengths. Um, but this is about as simple of an intake as you can get. It just has these two rollers powered by this is a 775 Pro, or a Redline. They were basically the same motor for the most part, just different or different company selling it. And so from here, you have a belt over. We can actually see they're using the smaller belt pitch than we think we've seen on almost every other robot we've looked at. So this is 3 millimeter belt pitch. We used to use this a lot when we had these smaller motors, because you could use this tiny pulley on them. We've pretty much stopped now that we exclusively use larger motors. We can use the 5 millimeter belt. They handle a little bit more torque better, and so they don't slip as quickly. We also just only have to stock one size of belt for each length. Same with pulleys and things, and it's just standardization has a lot of advantages in terms of cost and inventory, and spares and everything else. So we've standardized pretty much exclusively on 5 millimeter now for most of our robot parts. But this still does work, and we still have some 3 millimeter around that we'll use, especially for some prototyping things. We still have a bunch of motors that look like this too, that have this pulley on the end. And then over on the far side, so this is a live hex shaft going all the way through. They have the bearings here that the shafts are spinning in. And then they have the 5 millimeter pulleys on this side that are going to drive the lower roller here as well. This is all pretty simple to make, right? You see a ton of 1x1 extrusion, some small gussets. They run another 1x1 across to the other side to give it some structure here, since they're doing live bearings here. You want it, if you didn't have this beam here, it would be pretty easy for this to want to either spread or contract on itself. So this kind of sets the distance between these two outer plates. And they kind of just retract it back to where it's almost resting on the motors here. In CAD right now, it's actually going too far back, but they have plenty of room before they're out of frame perimeter. Similarly, down here on the pivots themselves, they're just running 3/8 round shaft into bushings on each end of these, with some spacers or possibly a thrust bearing here, or a thrust bushing here. It looks like just a spacer if it's hex. And then just bolted all the way through with a lock nut. So you wouldn't want to compress this too tight or to add a lot of friction, and it wouldn't be able to move well. So they just use the lock nut to be able to only tighten it down enough so it stops rattling or anything, and you can get some smooth motion out of it. And it's actuated with another pneumatic cylinder. So they have a cylinder block back here that they made to bolt through and kind of change the orientation of the cylinder so the pneumatic fittings are pointing up. If they were sideways, this arm probably runs into this front one, and so they needed to rotate it, while still getting this pivot point in the back here that I think is just bolted through this tube, I imagine. And then at the front, they have a rod end or a ball joint. And so this is able to kind of deal with some of the misalignment of this bolt as it goes without bending the cylinder shaft and allowing this to still move freely. This is a very efficient way to do it. And it does save you from bending some of these shafts and causing you to have to replace your pneumatic cylinders, if you're using pneumatics, to be able to have this super simple control without having to do basically any code to get your in and out positions or anything. It's just always going to push out until you run into your hard stop, which I imagine is what this is. And so this block is bolted to this tube and likely hits on their gearbox up here. And so you could change the size of this if you wanted to change where the intake was sitting when it goes and extends to grab the ball. So it's a relatively easy way to do that. And then back is probably just where the cylinder comes back. I don't see another hard stop. Oh yeah, either hard stop on the motor up here or where the cylinder is, depending on how much it works. So that makes sense. Um, okay, so that's a pretty easy one. They have the bumper cutouts there to allow the ball to smoothly come in. They don't have to ride the ball all the way up the bumper. They just have to get it up um, over this rail and then into the ball holder or scoring mechanism on the actual elevator. All right, going up a little higher, we have the actual elevator. Um, let's see how they're powering this guy. So this is down here. That's the compressor, by the way. So that's what's filling their air tanks with compressed air so they can use it with their pneumatics. And so down here, they have a small little gearbox. So they have these two 775 Pro motors driving a gear and then another reduction here, and then this chain, which is going to be powering their elevator. Again, they're using the smaller of the pitches, just kind of like they were using the smaller pitch pulleys with the smaller belt. They're using the smaller pitch gears here when we had these smaller motors. So this is 32 DP compared to our normal FRC gears, which are 20. And then now we also sometimes run the even larger gears, the 10 DP ones, for really big motion or for things we want to be able to cut out of the router. So like the shooter pivots and shooter turrets and things oftentimes even have the bigger gear pitch than that. Um, and so a lot of times when you didn't have as efficient motors and as powerful of motors, you did stack your motors together a lot more and combine them so you'd have double the power. So for an elevator like this, you would want to have two motors so that you could have twice the torque and you could move the system basically twice as fast while still being controllable and still having enough leader or headroom to actually be able to move it up and down in a controlled manner throughout the entire match. Okay, so let's see the rest of their motion plan. So there'd be a hex shaft running through this gear and sprocket into this bearing. This sprocket would connect to a chain somewhere up here. Let's see. Inside this tube? Yeah, there it is. Okay. So let's translucent that real fast. So we can see inside of here, they have a couple bearings. They have the top of that sprocket, so they would run the chain up and around that whole system. And they also have an encoder on this backside. And so this is what they would need to use to tell how far this sprocket has turned, to also be able to tell how far the elevator has gone up and down. So this definitely works. They would run this into either directly the RoboRio and sense it that way, or you could also run it into the data port on the Talon SRX, which is this motor controller here. So either one of those would work to be able to get the data back, and then they could do position control on it just like we do with any of the elevators we've built in the last couple of years. So you could tell it to go to any specific height throughout its range that you wanted, and the motors and controller would use this sensor to get it there. But you did have to use to design this in all the time, and these aren't encoders that are specifically built for FRC. So they don't have like a hex shaft input or anything like that. Same with like their actual connector back here isn't built for FRC. So what they ended up doing was just boring out the end of a hex shaft and having a set screw here that they tighten down to secure it to the end of the encoder shaft. And so then as that sprocket turns, this turns with it, and that sensor is able to read back how many times it's turned or how fast it's turning or whatever data they needed to get from it. All right, so that's how they're able to do the first stage. So they would have, let's see if we can't. where that would mount. I don't know where that would mount. Somewhere on that part of the elevator should be a way to mount to the sprocket, but I don't see a way to mount to the sprocket. It may be one of those ones that just didn't end up in CAD. Oop. This is not fully mated, so let me not drag things. All right, so normally you're going to have somewhere on this lower plate or this lower plate, you'd have a way to mount it to the sprocket down here. I'm unclear how they went about doing that from CAD, but it almost certainly happened. And then so as that sprocket turns, they're lifting up this next stage of the elevator. And so these bearings are going to ride on the elevator track as we'd expect. This is likely not there in real life. I'm assuming this gets cut off to allow the bearing to ride through, or you would jam your whole system pretty quickly if that didn't happen. And then they use this bottom lower connector plate to have their side bearings in here. Because the side bearings on an elevator like this, where you have a sideways elevator and your arm is hanging off to one or two sides, are going to be applying some amount of load, because this is always going to be, gravity's acting down here, kind of pushing this down. And so now this is kind of twisting, and each one of these is trying to almost pull forward by a little bit, depending on how heavy this mechanism gets. But that bearing stack's repeated on each of their stages. Gets a little bit different as we get to the carriage. They do some slightly different things with some 3D prints in here to be able to have smaller bearings on the outside here and some smaller bearings on the inside as well. And kind of see what that print looks like, that they bolt around the main plate for their carriage to be able to push the dowel rods through to hold those inner bearings. And then the outer bolts here and this plate hold in that dowel rod. All right. Now we talked about the bearings, we can talk about the rest of the motion system. And so, because we see this chain going up to that first stage and not continuing, there's not sprockets in other places, there's just these like pulleys. We can surmise that this is what we call a cascade elevator system. So the chain is only powering that outer stage to move it up and down. And then you have another inner stage, and finally what we call the carriage, that final stage of the elevator. And so to move this inner stage, we're going to have a pulley here that's on the first moving stage. And then we're going to have a pulley at the top of that first moving stage again. And so with that here, you're then going to be able to have a clamp point probably in here. I'm not sure if this is backwards. Might have been that plate, but there's probably some version of that, how that's happening. But basically this rope will be tied off in a way that's stationary to this bar, so that as this goes up, more rope is pulled down, and like this point doesn't move. The rope point in relation to here doesn't move. And so for the same thing, somewhere on, let's see if I can hide some things here. Somewhere on here, you're going to have a rope attached here as well on the opposite side. So we'll call this like on the right side here. And then up here on our, on this side, you would have an attachment point there. And so as you raise this whole section, the length between here and here and the length between the lower pulley and this one here basically have to be equal. So as one gets longer, the other one does as well. And this rises away from the from this pulley down here. So this allows it to go up. And they basically repeat that same process again with the pulley here and Mouse is not dragging. Okay, and here, and that gets attached into the back side of the carriage. Um, these are the air tanks. I'm about to hide them, but these are where they accumulate air for the pneumatic system before they use it. And there would be an attachment point to the carriage, um, potentially around one of these hex shafts or on one of these plates. Ideally, you want it perfectly in line, um, so that you're not changing any of the distances as they get farther or closer to the pulleys. But it doesn't always happen that way. Um, and so that's how they're able to move each of the stages of the elevator. What that means is that you can't just move the carriage up without moving any of the other inner stages. Each one of these stages moves up. So, like, if this one moves up an inch, then this one also moves an inch, and this one also moves an inch, and everything has to be equal in that way. Um, and so you do end up having this part of the elevator stick out rather high before you actually get the ball up rather high. So sometimes that's okay, sometimes it's not, and you can decide how you want to run an elevator. There's two different ways to do it. That's cascade. Continuous is what some of the ones that we've seen before, where it has the belt or rope or whatever mechanism they're using, kind of snaking its way through each level. And in that case, you can have the carriage just go all the way up first, and come back down without moving any of their stages. Um, okay, they have a couple other little details. They have their network switch and radio mounted relatively high, out of the way of other motors and things. That's normally what you want to do. All right, we can look a little bit at how they construct the carriage itself. So this is all basically constructed out of flat sheet, with that little bit of 3D printed parts in there to help, and some hex shaft running across the back to space out the sides. Oh, and we can see in here they sort of uh, place in. They have this cutout in the white or in the yellow plate to be able to place this 1/4 inch main plate inside of, to be able to give it that strength to where this can't move in relation to this plate. And then they use the L bracket to actually completely fix it. Um, and this allows these bearings to be bolted to the same assembly that bolts in these plates. And you kind of tie this whole setup together very nicely, and securely, and it should be pretty rigid here to be able to do that. Um, Depending on what you're trying to do, you could make this a little bit thicker too. But they do have even a larger standoff down here to add some stiffness to this. How do they do that? Is that cut? Oh yeah, that's a full rod. That's not just a tube. And they're bolting up to the inside of that as well. So that's going to give them a lot more stiffness, um, on this carriage assembly now that they have this whole rod here. So I don't know if that was the original design. They have it here too. Um, but that's going to provide a lot of stiffness between these plates to where you're not going to be able to really bend that, as you have these sticking in here and you have these large standoffs in addition to the standoffs in the back right at these bearings. That's going to hold it together very well, so you're not going to have a problem with it like flexing and having the bearings potentially pop through the elevator, which can be very annoying if you're not resting in the right spot. Ooh, I still want that one gone. So you wouldn't want to have like this bearing be able to like come through and push through, or your whole carriage could slip out of your elevator, which can happen. And so depending on how much bearing overlap you have, and how stiff your carriage can be, kind of determines some of that, and how tall, kind of the dimensions of it as well, determine how easy it is for that to potentially happen. It can potentially rock or twist inside, of the rails too, depending on how stiff the rails are. There's a lot of little details that can happen to make the elevator not quite work the way you want it to, um, if it's not built correctly and it's not tested and iterated correctly as well. Um, Part of the key design of this robot is the ability to have this wrist swing, forward and backwards so they can score on both sides. And so they definitely, just from this, you can tell they're clearly designing the carriage to be able to do that. These two horizontal plates are integral to it. A lot of times you'd end up if it was a normal kind of straightforward elevator and you just had an intake on this side, you'd want these plates to be a lot stiffer, as these are where you're going to be mounting things to. You might have your motors in that direction if you have a wrist going up and down from there or anything like that. But since this is the sideways mechanism, you have these top and bottom plates. In here we have that same 775 Pro motor with another gear reduction um, going down here, um, and then geared, and then geared again down to the actual horizontal wrist motion that we get here, where we're going to have that swing arm going around. We again have an encoder mount down below. In CAD here, it just has the bolt here. It's possible that they extend that shaft through to get the encoder. That's my guess as to what's happening. But we just don't see it in CAD. To actually do the arm itself, they just have a gear mounted to the box tube. They go ahead and have standoffs on the inside and a backing plate. So this gives them a little bit more support right on the wall where you need the strength, because this is where you're twisting the whole rest of this arm. I'm going to see this is also supporting what I assume to be the bearing. Yeah, so you have that bearing here. No, so this is a dead axle. So I actually don't know how this encoder is working. I take that back. So this is bolted fully to this assembly because there's no bearing here. So because of that, this rotation is only happening around this shaft, and this shaft isn't rotating. So we have the two bushings here going through the gear face and into this plate. And so this encoder is in theory trying to read this arm, but I'm not sure how they're... Okay, so yeah, so they would need to have some... Yeah, yeah, so they'd have to have some way to gear this somehow. They could gear it to here, and then they would just be getting... Yeah, if you have the same gear size to here, something, or I guess a similar one, you could gear ratio and still get the logic for how this gear is rotating. Is it somewhere else? No. All right. Okay. So the rest of their motion system is basically these wheels out here on their actual intake, and then the mechanism they use to actually grab the hatch. So inside of here, they do some more work inside of this tube. So we can transparent that, and we can see that they have a bag motor. So this is another type of motor that you could use. These were styled similar to the Sims and the mini Sims, but they did not. They were much, much smaller. These are about the diameter of the new Kraken X44, or at least similar. And they again have a tiny pulley, tiny 3mm pulley driving this larger pulley here to get that gear reduction. And then again, they're just doing the power transmission, and they're actually doing that inside of this tube. So if we stop making it transparent, you can see that it's all happening inside the tube. That potentially makes maintenance a little bit harder, but it does make it so it is less likely to run into anything. You're not rubbing it on the balls. It's pretty hard for it to slip off since it's running inside of here. And it's not too bad. You have enough space inside of this 2x2 to be able to feed the belt down and kind of get the pulley and shaft around it, and do the same thing up at the front. Yeah, so this is live axle. We have our bearings here, pulley, hubs for the wheels to be able to turn at the same time as that hex shaft. And then up top, this is one of the more interesting mechanisms, and a lot of teams did this differently, but they're all basically the same idea. They're grabbing the center of the hatch. So in this case, as this pneumatic cylinder was pulled back, these bolts would be able to slide, and these would point out towards the front. And so you'd have them sticking out this way. And so then when you push the pneumatic cylinder forward, they would then go around the arc. So these plates are pivoting on this blue bolt, and the slide is allowing that linear motion to turn it into rotary motion. Hatch panel and holding it on. So the hatch panel itself would be resting here between these two plots, and then same on the other side. And so it's impossible for it to come out until they retract that cylinder again and drive backwards. That hatch is going to be stuck fully into this mechanism. So as they swing it around or anything, you're not going to have a problem dropping it or anything like that. Let's see, the last little bit. So they have the ball holder down here. This is a relatively simple part of the mechanism. It's just some 2D cut parts, polycarb or aluminum, whichever they want to use, with standoffs between them to give it enough length to kind of get the ball in place. The gap probably helps center it a little bit to get the ball sitting inside that main groove most of the time. Since as they're spinning it, it's going to want to kind of spin in and sit inside that wider channel a little bit. All right. Most of the things that are on this robot are relatively simple to make. So a lot of the C channel and things that are things that you could, drill yourself pretty easily. You can produce this. Same with these brackets. These aren't things that are all that difficult to produce by hand even. You may not even need to do a CNC to build a lot of these things. Some of these plates you'd want to get cut somewhere, but you could do things like print a one-to-one template out and drill and cut them and kind of trace them. There's a lot of ways you could do this without a ton of CNC work. You don't have to like water jet all of these parts very much. You could use a 3D printed template for some of these smaller ones and still drill and cut. Or doing, nowadays you can do things like FabWorks or Send Cut Send and have parts made. And so even if we don't have expensive CNC tools, or if ours are down or something, there's still a lot of ways to make some of these parts, or if we just need to prototype them, we can make a lot of these pretty quickly. All right, so last on the list for this robot is their end game mechanism. I believe this was added. I don't think this was on at the beginning of the year, but it's basically these two tubes down here on the side. These are connected to wheel platforms at the bottom. So this front one has small casters here that are unpowered, just like this. And then the rear one has another bag motor here. This is a versaplanetary gearbox. So this is similar to a max planetary, but it is smaller and designed for these like smaller motors. We use them a lot for prototyping still. We haven't had one on a robot in a while. Probably won't, but they work great for prototyping, and especially if you're using the bag or 775 Pro motors, these are very useful. You can get a lot of reduction the same way you can with the max planetaries. You have these planetary gears going and doing your reduction here. From that output, you have a nice 1/2-inch hex output, and they just have a belt drive to another set of wheels. So there's two more Coulson wheels, and these ones are actually move them. And so to be able to actually push up and down, that's what this thing in the middle that we haven't really looked at yet is. This gearbox here and these two spools are for string to be able to pull down the these two arms and raise the robot. So it's a relatively, this is a COTS gearbox. They had a 2-to-1 adapter for the versaplanetaries. So you could have two 775 Pro motors driving a small gear here that then drives the versaplanetary and drives the spool. They also have a little ratchet mechanism that existed. So this is a ratchet slice that potentially allows it to lock itself into place. They use chain and sprocket here because it's high enough torque and load that you wouldn't want to use a belt. The belt might just slip. You're trying to lift the whole robot with this. And this is all mounted under their belly pan. And so the spool cable, um, one side is going to go through either one of these holes or through one of these openings. I'm not sure which way. And then same on the other side. It's probably going to go through one of this main opening here. They may have added things at some point to help guide the wire or guide the rope. Sometimes it's as simple as like tape just to make sure it's not getting cut. And so up at the top here, we have another set of pneumatic cylinders, these little pancake ones that push in and out. And then there should be somewhere down here, there would also be a spring that is pulling up the arms when it's released. I don't know if I see where the springs mounts, but it's in there somewhere. And so basically you'd have that string attached up here. You'd have a spring always trying to keep these up. So the spring's always pushing these up, likely pulling these up from the bottom and holding them in while you're driving around normally. And then when you go to actually climb, your spool would be spooling from this pneumatic cylinders. You'd have like a loop attached across here, and these would be pushed out at the beginning of the match, and you'd pull both of them down. So the strings would be pulling in, and you'd pull down on both these tubes. They slide on another bearing stack. It's missing, it's probably just bolts going all the way through in this case. And so then these would be sliding down. The robot would raise up. As soon as the bumpers are above the level 3, you would be able to drive using these back wheels, drive it forward. You get your front wheels to actually support yourself on the top of that platform. And then this is where you use that pneumatic cylinder. You'd be able to release it. So you basically drop the string, and now the spring up here is going to pull this back up. And so then you can drive even further forward. So you could get your middle wheels onto the platform, and you can go even further forward. And they use this little pneumatic device here to help make sure they didn't fall backwards once they were about to lift their rear wheels. So they would push this down onto the edge of the platform so they wouldn't rock back. And then they would release the string again. And so then this would just shoot back up by the spring, and they'd be stationary on that top platform. And then once it was all the way up, they could drive forward fully onto the platform. And so this was a relatively compact way to do that level 3 climb. It allowed a lot of different options for teams that did something similar to this. So this is similar to the climb that 3310 did. It's packaged a little bit differently, but it's the same concept where you stick down 2 different sticks with wheels on it, drive forward, lift one, drive forward again, lift the other. And so it's a relatively simple to do. They do have to make sure it's strong enough in here that you're not going to be bending this too much, because you are only supporting it on like one side. That's also where a lot of your weight is as well. So you don't have a ton of weight over here on this outside trying to bend it and having it fall over the other way. Yeah, so that's pretty much the entirety of that robot. You could imagine you could do this the same concept if you had weight and motors. You could independently power each one, so then you could bring one up and down independently. You may not have to use the pneumatics to drop your strings, but that kind of just depends on what you're trying to do. They also may have wanted the spring version because it may be a little bit faster. Once you're up, you're never having to use motors again. You're just releasing those pneumatics, so you should be able to drive on a little bit quicker possibly. But it just kind of depends on how you gear everything, how you set it up. But there's a lot of different options and things like this. All right, I think that about sums it up. There's a few little things as well we didn't talk about. So they do support the elevator back here with these rails going down, and they use that for more mounting as well. So they do have this like side mounting rail here that runs over their wheels and backs their bumpers. They do that on both sides. And they do have a very simple limelight mount up here where the limelight is just mounted to a piece of 1x1 aluminum and drilled into the elevator. Not entirely sure how they stop it from pivoting down. Um, they may have some sort of zip tie up here or maybe another hole that's just not in CAD. Um, but this does give them a couple limelights looking down. This is likely for the sandstorm and for driving, um, possibly looking at like detecting the ball or looking at the vision targets as well. So there were vision targets on the um, rockets and on the cargo ships. They have these like angled um, this angled vision tape, the retroreflective tape, and so then they were able to see and line up to those vision targets automatically, and so that helps a little bit to get in line. Again, it's nowhere near as easy as it is with Swerve now, because Swerve you can just drive up and be really far off. You can just slide sideways. You do have to kind of like aim from farther back so that as you drove forward, you were hitting the vision target correctly. All right. Let's see what else. Oh, we didn't talk about up here. So there's some constant force springs here assisting the elevator. So these are raising um, the carriage and taking the weight of the carriage. Um, because it is cascade, these constant force springs are helping the entire system. Because as they pull up on here, the whole system does want to raise because everything is connected together each stage. Um, and so that allows them to spring assist their elevator, make it a little bit easier to control. They're having to lift less mass since the springs are helping with that. Um, and kind of always pulling the elevator to extend it. I think I haven't missed too much else. No, I think that's the end.